I have it recording on my computer now. Good. So yeah, guys, welcome. So glad that you guys are here. Super happy to kick us off. We're just going to be talking about, well, kind of some of the fundamentals. A lot of what you're going to be learning, I think, in the next 2 or 3 days even, kind of carries a lot, if not just like for the sake of intuition, building, then actually in techniques that we use in the field to uh, kind of bring to light the new research that we're doing. So let's go ahead and get started. First of all, let's introduce C-star algebra as the topic that we're talking about in this particular lecture. So C-star algebra is a multiplicative, involutive Banach space whose norm satisfies two conditions. The first one is submultiplicativity, which really says that this is a Banach algebra. Says that if you take a product of two elements in your Banach space, then this needs to be bounded by the product of the norms. And the second condition is the C-star identity, which tells us that if we look at this involution, which is an operation which is denoted by star, this is an antilinear operator, and you compare the product of an operator A with its adjoint, this is required to be exactly the same as if you take your operator A and you just square it. Um, we're going to see time and time again, especially in this lecture, that a lot of special things follow from this identity, which really distinguishes it from other Banach algebras and things like this. So one thing that comes immediately from this is that actually this involution, this antilinear operation that we were talking about, is actually an isometry. This implies that the adjoint is an isometry. So we can see that A is less than or equal to A star just by applying both the submultiplicativity and the C-star identity. And then likewise, we have that A star is less than or equal to this quantity A star star, which is just A. So you put these two inequalities together and you find that the involution is an isometry. Good. So we'll kick it off with a handful of examples, which are going to come into more and more depth as we continue these lectures. So we're going to start with an example coming from the pre-lecture notes. If you look at the bounded operators on a Hilbert space, these are the bounded or continuous or the continuous at zero operators, T going from H to itself. And also, oh, and of course the norm is given by the operator norm. And the involution is given by the Hermitian adjoint. Which says that T star against a vector X takes exactly the values of T applied to X and the other factor of the inner product. Okay, so this operator norm exactly satisfies the C star identity. And this also tells us that any closed star subalgebra of B of H is also a C-star algebra. But these are far from our only examples. Another example that I rather like, uh, and we're going to get a lot of legroom out of, comes from when we take X to be a locally compact Hausdorff space. And you look at the space of continuous functions on X, which vanish at infinity. The functions from X to C, which vanish at infinity. Um, yeah, the norm is actually given by the supremum norm. And the adjoint is given by f star evaluated at x is exactly just the function, but then you take the complex conjugate of it. So then you can see quite quickly that if you take f star f and you evaluate that at a point x, that's the same as if you had taken the absolute value of f and squared it and then evaluate that. And then when you compare the norms, f star f is just the supremum of all the values as you look along the topological space x. That's exactly the same as the norm of f squared. So it really comes up rather naturally. Uh, Taking a little bit of a more specific perspective, we can take T to be the unit circle in the complex plane and look at the continuous functions on the circle, right? These don't need to vanish because now we're looking at a compact space. And we can investigate this just a little bit more closely. If we define a function, I'm going to call it zeta, and it's going to go from the circle to the complex numbers. And it's given by, you give me any complex number on the circle, I'm just going to tell you what it is. It's just the identity function. Okay. So there's some work done on, trigonometric polynomials, which basically says that any function which is defined on the circle is given by is a limit as n approaches infinity of some sum of alpha n times different powers of this function zeta to the n. Sorry, don't want that. Let's go from minus k to k. We want k to grow up to infinity. Okay, so we can actually look at this and recognize that the continuous functions, said another way, what I really want to say. If we look at the star algebra, the algebra, which is generated by both zeta and zeta inverse, well, if I want to say that, that's the same thing as the algebra generated by zeta and zeta star. Then this says that its closure is actually the circle. Closure is the continuous functions on the circle. So actually, this is generated by a single operator. So C of t is generated by zeta and its adjoint. Okay. Just one more example, we can take a little bit of inspiration from this. And one of the operators that we like to play with comes from kind of a blend of this of the bounded operators on the Hilbert space and some of these techniques that we're looking at now. You take the shift operator defined on L2 and n to L2 of n, given by S on EJ is exactly EJ plus 1. This is the right shift. So you can kind of play these games the same way as we pay attention to, how maybe a single operator could generate an entire class of functions, say on the circle, you can say T is going to be the set of all, well, it's going to be the closure of the algebra generated by S and its adjoint in the bounded operators on L2 of N. This is called the Toeplitz algebra. Which exhibits a lot of different structure, which kind of blends these kind of feelings of being matrices where you have non-commutativity. For example, S star S is not equal to S S star, which is exactly what we had up here. We had that zeta zeta star is equal to 1, the constant function, the same as zeta star zeta. So these are just some nice examples that maybe you'll want to keep in mind as you're studying different C-star algebras, because working with actual examples just brings a lot of inspiration for us. So let's get some more definitions down. By the way, you guys can interrupt me at any time. So a C-star algebra is unital, provided it, well, it has a unit, meaning there is an element which we'll denote by 1a with the property that 1a times multiplication on the right is the same as multiplication on the left by this thing, 1a, and that's the same as this thing, the original element for any operator in your C-star algebra. Okay. From this, it should be rather clear that 1 has the property that 1 is its own adjoint, and also 1 has norm 1. This follows from the definition of, well, it being a unit, right? Just compare 1 times 1 star is equal to 1 star. And then find it. This isn't worth too much time. It's written in the notes for sure, and you can just run a little bit of
You can
upgrade.
like use the the star of AB equals B star A star, I think, right?
Yeah, that's pretty good. But anyway, I don't want to fuss with it too much. And then this follows exactly, once you know this step, it follows from the C star identity. Thanks, Nick. Good. So that's unital. And we take this time also to define a bunch of other, well, to give a bunch of different names to different operators. So further define for an element in a C-star algebra. So we say A is normal if it commutes with its adjoint. It's called self-adjoint if it is equal to its own adjoint. It's called a projection if it is a self-adjoint idempotent. It's called an isometry if the product of A with its adjoint uh, on the left is equal to the identity. It's called a partial isometry if A star A, this triple product is the same thing as the operator that you started with. Some things that you want to think about, probably it's worth taking home later tonight and just before bed and meditating on when a normal element is self-adjoint, just kind of teasing out the different relationships that we have between, say, projections and isometries. Like one question we can say is, given A, let's let this be in a different color. What can we say about A star A? Is it normal? Is it self-adjoint? Is it a projection? You can just ask these kinds of questions and fiddle with things.
For the projection, we want A equal to A star and A equal to A square, right?
Yes, thank you. Yeah, self-adjoint and idempotent. Good. So yeah, let's get into a couple of facts, which well, let's just get into them. So given any operator in a C-star algebra, it is a sum of two self-adjoint operators, namely the real part of A, which is defined in exact analogy with what you do for the complex numbers, is you take the sum of A with its adjoint, which for complex numbers would be the complex conjugate, and you take the imaginary part to be the difference, where you divide by 2i, A minus A star. Okay. So this fact, it tells us that it's really instructive for us to study the self-adjoint elements and what they have to say. In fact, there's a whole field which tries to kind of ignore the algebraic structure and just pay attention to this self-adjoint structure to determine what information can be said about these operators or how they connect with one another. Um, so let's okay, so let's finish this thought though. So then you can write A is equal to the real part of A plus I times the imaginary part of A. Okay, so let's get a proposition in. Like I was just saying, studying self-adjoints should give us, well, happens to give us certain information about the actual algebraic structure. So this proposition tells us a linear map between C-star algebras is star preserving. So that means that pi of A star is equal to quantity pi of A with the star on the outside, taking the adjoint from the image. So a linear map between C-star algebras is star preserving uh, if and only if it maps self-adjoint elements to self-adjoint elements. So we can take a proof. The forward direction is rather obvious, right? So if it preserves adjoints, then of course pi of A star in here is going to be, sorry, let's put it this way. Uh, if A is self-adjoint, then pi of A star is equal to pi of A, but it preserves, I'm not doing this quite how I'd like. So let's do it one more time. Pi of A is pi of A star, and as it preserves stars, that's pi of A star Hmm. Of course. This is it. This does it. Yeah,
Yeah, that shows pi of a is self-adjoint.
perfect. Good. So then going the other direction, this is where you end up needing a little trick. For the reverse, if we assume that it sends self-adjoint elements to self-adjoint elements, you let A and A and write it as the sum of these two self-adjoint guys. A is equal to the real part of A plus I times the imaginary part. So then you just notice that pi of A star is pi of this real part of A plus I times the imaginary part of A. All of that is getting adjointed. Well, all of the operators involved are self-adjoint, so they're not going to do anything. But the adjoint is an anti-linear operation, so it's going to reverse the I to a negative I, right? So it's going to be pi of real of A. We'll just do this all at once. Minus I times pi of the imaginary part of A. But of course, that's the same as pi of bilinearity. Ah,
Real part of a minus the imaginary part of a, which is a star.
plus I pi of imaginary of A. That gets starred. There it is. Pi of A star. Just like that. Thanks. Um, good. So this already tells us that it's instructive to be studying at least the self-adjoint elements. And in fact, just an Easter egg for later, we can notice also that A star A is uh, is always self-adjoint. Okay, so let's go ahead and move on. Uh, so one of the historical objectives that people have done when they've studied, operators acting on a Hilbert space or on a Banach space or whatever, is studying them based on by investigating their spectrum. You guys, I guess, must have seen a little bit of this from the prerequisite lectures and from the prerequisite notes as well. Um, so let's go ahead and hit it. So if A is a unital C-star algebra, do I want to say even an algebra? You don't even need any structure. It's just a unital algebra, and A is an A. We define, well, we say first that A is invertible if there exists another element with A times B is the same as B times A, which is equal to the identity in that unital algebra. Okay, we define the general linear group of A just by analogy. It's just the set of all invertible elements. It is in fact a group, but that's rarely do I want to say rarely? It's not instructive, at least for us today. Mhm, mhm. Good. So let's take an example. Unitary operators. Remember, that means that A star A is the same as the identity, and that's the same as if you reverse the role or the positions of A star. So these are invertible. Another example is if you take the same A, then 2A is invertible with inverse 1/2 A. So we can kind of see, well, let's actually just take even one more example. If we take a function which goes from the circle and its values are here from 1 to 2, say.
In the above one, shouldn't the inverse be half A star?
Yeah. Well, not, yeah, star would do. Yes, good. Thanks. Good. So if we take a different operator, say it takes the values in 0, 1, or in 1, 2, then we can see that 1 over f is a well-defined function going from the circle, and its image is in 1/2 1 instead. But so I'm just trying to really kind of paint a picture here of the diverse ways that an operator can be invertible, right? So for unitary operators, it turns out that its adjoint is actually its inverse. But if you take an operator like this, then this f is actually self-adjoint. And that adjoint is not an inverse. So there are many ways to actually find inverses, some of them coming from studying actually like the images. And there's this relationship here saying, well, f goes from 1 to 2, then 1 over f should go from 1/2 to 1, right? In this way that you get this cancellation point-wise. Good. Okay, so that's invertibility, and that prepares us to actually define the spectrum. Spectrum of an element in a unital C-star algebra. Spectrum of an element in a unital C-star algebra. Good. So the spectrum of A. So given A in this unital C-star algebra, define spectrum of A to be the set of all complex numbers where lambda times the identity in A minus A fails to be invertible. Okay. Yeah, so it turns out that this failure to be invertible has a lot to say. Like, for example, taking this example with this function from the circle, this function f would be invertible everywhere, right? Because the values that it takes are from 1 to 2. So it's inverse. You just invert pointwise, and then you get an operation, or then you get an inverse. However, if this function f happened to take the value of 0 anywhere on the circle, then it would fail to be invertible at that particular point, right? Because you can't divide by 0, essentially. So there's no inverse for that particular function. The analogy also goes pretty strongly with matrices, right? This is how we can look for eigenvalues essentially as well. And a bunch of linear algebra course is all about studying the eigenvalues and what the eigenvalues have to say about the operator. Let's see. Okay, so let's do a quick example. I want to do a quick example. Now let's just write this. So example. Of course, more details can be found in the notes that have been provided as well. If U in this unital C-star algebra is a unitary, that implies that the spectrum of U is exactly confined to the unit circle. So we can sketch this real quick. So there's an identity U minus lambda I equals, yeah, let's actually just show a little bit of detail in this identity. Lambda U, lambda inverse I. Of course, everything multiplies to 1 there, and we're going to subtract lambda times U star. And then just doing a little bit of algebra, we factor everything out. That's lambda U times lambda inverse times the identity minus U star. So it follows from this that the right-hand factor, lambda inverse I minus U star, is invertible if and only if the product of U minus lambda I against lambda inverse U star is invertible. Remembering some things from the prerequisite notes, just as an operator in a Banach algebra, if we're in the spectrum of an operator, then the magnitude of that element of the spectrum is less than, it's bounded by the norm of the operator. So what this identity basically tells us is that if we are able to avoid the spectrum of U, then since U is a unitary, so it's invertible, then that inverse of the eigenvalue, or that inverse of the element of the spectrum is going to allow this operator in red to be invertible. So basically, it follows that lambda needs to be less than 1. Well, the value, then the norm of the unitary, which is equal to 1. But also lambda inverse needs to be less than the norm of U star, which is also equal to 1. So that tells us that lambda needs to be an absolute value 1 whenever we actually do land in the spectrum. Okay. So good. This is how we define the spectrum of an operator when we're in a unital C-star algebra. We have this problem that not every C-star algebra is actually unital. It's an obstacle. We want to treat it that way, that this is an obstacle to us getting to the spectrum of an operator. Right? Not every C-star algebra is unital. So how do we define the spectrum? So what is the spectrum, which needs invertibility?
Actually, can I make a brief remark? I think it should be less than or equals above, right?
Yeah, you're probably almost surely right. Thanks. Did I get that? I guess we want that there. There's the last one. Yeah, should definitely be less than or equal to. Thank you. Good. So we could even we should take these examples and carry along with us. Consider the continuous vanishing functions on the open interval 0, 1. So this doesn't have a unit because it's projectionless. No unit, projectionless. Another example of a non-unital C-star algebra of huge importance to me anyway is the compact operators on a Hilbert space. And you can see in the lecture notes proposition 1.14, any candidate for the identity is exactly the unit on the bounded operators on the Hilbert space. And of course, that would be a problem. So since the compact operators is an ideal, then everything would collapse, right? As soon as the unit of the whole thing is in the ideal, then the compact operators is everything. This fails for the dimension of H, say, how about equal to infinity? Okay. Nevertheless, there's something that we can do. In this first example, we can consider that the continuous vanishing functions on 0, 1 actually sits as a C-star subalgebra of the continuous functions on the closed interval from 0 to 1. So we can consider a subalgebra, the set of all f plus lambda 1, where f is in C0 of the open interval and lambda is a complex number, where 1 is just the constant function. Okay. So you can do is you could look at this. This is a self-adjoint subalgebra of the continuous functions on the closed interval from 0 to 1, but it doesn't separate points. Namely, it doesn't separate, let's be a little bit more particular. It doesn't separate 0 from 1. Nevertheless, you can ask what its closure is by Stone's-Weierstrass. This closure is the set of all functions in the continuous functions on the closed interval with f of 0 is equal to f of 1. Okay, similar trick, we do it on time, is in the non-commuting setting, is we can still recognize that the compact operators does reside inside of a larger C-star algebra, right? Subalgebra of the bounded operators. So we can try and access that unit. Again, you can consider the set of all, what am I doing? T plus lambda identity H, where T is compact. And again, lambda is in the complex numbers. And this is, again, a self-adjoint subalgebra. of B of H. So all we have to do is close this up, and then since any closed star subalgebra of B of H is a C-star algebra, then we've basically done our job. This allows us a unit. Remember, the whole reason we wanted a unit is so we could study the spectrum of these different operators. So you can take this analogy in these two examples and extend it to any C-star algebra in exactly this way. Remember, all we really did is we said, well, we're just going to find a place where we can find an identity, and we're just going to add that thing in. The unitization of a C-star algebra is the C-star algebra. This is actually a claim. A direct sum the complex numbers with coordinate addition and product, which is a little bit unconventional, but thinking in the view of these models that we had above, you can take A with lambda and you can multiply it against B with mu. And well, you treat these things actually as binomials, right? And so what would you do with a binomial is you'd actually want to FOIL it out. You'd want to multiply them term by term. And this ends up being AB plus lambda B plus mu A plus,
No, that's it. And then you'd have the lambda mu as a separate coordinate.
yeah, you're right. Let's put that in quotes. And then we actually write it AB plus lambda B plus mu A, comma, lambda mu as a separate coordinate. Good. So this is actually a claim that this is a C-star algebra. Sorry, here. Oh, let's give it a norm too. And norm, A lambda is given by the supremum over elements B and A, which are bounded by 1, of AB plus lambda B. Okay, and proposition 1.18 from the course notes tells us that A embeds isometrically into a direct sum C with the above operations. Good. As an ideal of codimension 1. So we denote the unitization by A tilde. Just going to leave a couple of comments on this proof. Really, the only tricky thing is the norm. But in the context here, so we define this norm to be related to exactly the norm coming from A. And so because you know that in A we have a C-star norm, you kind of just pull this back with us to get that the norm that we define above is a C-star norm. That's the idea. Okay. So one other cause for concern is that if we pass to unitization, maybe it behaves badly with star homomorphisms or something like this. Like if you start with a non-unital C-star algebra and then you consider its unitization, well, is there a nice way for us to extend the star homomorphism that we had from A to B to A tilde, right? But the proposition 1.22 says that there's no problems, really. Let's see. If A is non-unital and pi is a star homomorphism going from A to B, then there is a unique star homomorphism pi tilde going from A tilde to B tilde with pi tilde of A plus lambda times the identity on this unitization for A is exactly pi of A plus lambda times the unitization for B. So basically, this is as good as you could hope for. And with all this unitization stuff in hand, we can define the spectrum for any. For A, where A is any C-star algebra as follows. Sigma of A is the set of all lambda in the complex numbers, where lambda times 1 for the unitization minus A is not invertible in the unitization. That gets us back where we need it to be. Okay, in the last few minutes, I want to try and return to the C-star norm and see a couple of extra implications that we have now that we've developed a little bit of machinery and related the spectrum of an operator in C-star algebra to some more analytic features. So let's just recall one more time the C-star identity, which I like to interpret as uniting some of these algebraic features. So like having this involution here and this multiplication, it relates it to the norm structure, which is inherently kind of like a analytic structure, something coming from functional analysis. And now that we've got this notion of the spectrum, which is relating invertibility, which is inherently an algebraic concept, right, can be defined for any algebra. Well, in the presence of these algebraic features or these analytic features like the C-star identity, you see that you get a lot of power. So let's just recall a couple things from the prereqs. That for any Banach algebra, A and any element in that Banach algebra, the spectrum of A is confined to the ball of radius given by the norm. This is all in the complex numbers, right? It's always confined here. It's closed, non-empty, compact. That in itself, non-empty is the remarkable part there. And if R of A is the supremum over all these lambdas. Oh, supreme of the moduli of all the lambdas in the spectrum. It's called the spectral radius. Then yeah, R of A is less than or equal to the norm of A. One thing that's important about the spectral radius, that's one thing from the pre-lecture notes, is that in any Banach algebra, R of A can actually be computed as the limit of powers of A, and then you take their nth root outside of the norm. So I'm going to leave with just a couple of theorems which show how these two statements can be upgraded when you go from any Banach algebra into the realm of C-star algebras. So we're going to isolate this one first. If A is any C-star algebra, and A is a normal element therein, then not only do you have this inequality, but it actually turns out that R of A is actually exactly recovered by the norm of A. So once again, we have this relationship. The spectral radius is saying something about the algebraic features, right? It's saying something about invertibility. And meanwhile, the norm is saying something about, well, the analytic structure. So this builds a strong tie between these two features, at least for normal elements. And then I want to make sure that you guys have a little bit of time to rest before the next lecture. So I'll leave you with one other proposition. 1.29. By the way, this was 1.28. This is lemma. 1.28 in the lecture notes. Proposition 1.29 says that any star homomorphism pi going from A to B between C-star algebras is contractive. It's i.e. the norm of pi is less than 1. It only shrinks and is hence continuous. Moreover, yeah, any isomorphism, star isomorphism, is isometric, which is a huge departure from the general Banach space or Banach algebra setting. Okay, so unfortunately, I'm going to have to skip the proofs of these two lemmas, which makes important use of the C-star identity together with these algebraic notions. But as you guys go through and read the notes, I just want you guys to emphasize the interpretation of the relationship between the norm structure that we have on one hand and the algebraic structure that we're studying on the other hand. So with that, thanks, guys, and hope that you guys enjoy the next 2 weeks. Also, I'll stick around for questions for a little bit in case anybody has any.
Thanks, Lucas.
Yeah, of course.